Buckle up for a bit of a long one and potentially a difficult one. So we've got our overall spider diagram that shows all of our basic reactions here that we've covered. For the most part, we've really addressed these upper ones, looking at relatively strong nucleophiles and how they would react with just a carbonyl. What becomes problematic is when we move to this lower half of this, we're going to change, and instead of looking at just a carbonyl, we're going to add a nonpolar pi bond just one bond away, which means those two are conjugated. That conjugation or that proximity changes the chemistry a little bit, and that's a chemistry that we're going to have to watch out for. For those people being like, well, dang, why should it possibly change the chemistry? The easiest reference that I can give you is that if we have an OH, we might say, well, that's an alcohol. But is it an alcohol? That's still an OH, but now that it's next to a carbonyl, that functional group is now known as a carboxylic acid. So when you bring your functional groups close to each other, it can change their overall chemistry, and this is no different. So we're looking at this kind of new-ish functional group. It's typically referred to as an alpha-beta unsaturated carbonyl, which is a lot of words to pretty much say we have a carbonyl, and if we look at locations, the next carbon over, nomenclature-wise, is alpha. The next carbon would be beta, so it's a naming system. Okay. Between the alpha-beta bond, we have that nonpolar pi bond. So what we've now done is unsaturated that structure. So it's an alpha-beta unsaturated carbonyl. Okay. So let's see how this would change things. So if we look at our resonance structures between this, hopefully what we notice in these kind of nice already drawn diagrams is that we get a couple different reactivities. Okay, so the first resonance that isn't actually shown on here is that if we had just done the carbonyl, we would have ended up with a positive charge on that carbon and a negative charge on that oxygen. If we do the resonance where we see how that pi bond incorporates, we now see that negative charge on that oxygen, not a big deal, and a positive charge on a different carbon. And now that becomes the big issue. Because remember, when we were looking at the carbonyl, we weren't too concerned about the oxygen's reactivity because it was primarily just going to act as a base. The carbon, however, could act as an electrophile. With the alpha-beta unsaturated carbonyl, there are now two sites that a nucleophile could attack. Which site becomes the important one? And that is really kind of the crux of what this video is looking at. So we have to be a little bit more careful when we consider these reactions. Depending on which way the nucleophile attacks, we will call that a different name. So this is where you'll hear the direct addition or a 1,2 addition, or you'll see conjugate addition, which is a 1,4. That naming system gets a little bit odd, and we will kind of reference that. But let's take a look at the easy one first, our direct addition. If we evaluate that, come on down. Our direct addition is saying that we're going to add something here, primarily our H, and then our nucleophile. Okay, so if we look where those things added, it's at an arbitrary position 1 and an arbitrary position 2. So these aren't nomenclature numbers, they're just a reference point. So in the direct addition, we're doing, well, a direct addition to the carbonyl. Okay, so we're adding at position 1 and position 2. The conjugate additions become a little bit trickier to recognize, but if we go through and look at that resonance structure, this is what helps us. And we're going to kind of use quotes on this because the conjugate addition actually gets hidden. We're taking that negative and placing a hydrogen, and we're taking that positive and we're placing our nucleophile. If we now go through and count this out, 1, 2, 3, 4, we've added something at position 1 and position 4, hence the 1,4 addition. And we'll see why that 1,4 becomes less clear or less obvious in a little bit. First, we actually got to run a reaction with that. But that's where the naming is coming from. It's referencing the two reactive sites within the alpha beta unsaturated carbonyl. So you've got those two electrophilic sites. Yes, they're only 3 positions away, and that makes the names kind of confusing a little bit, but be kind of aware of that. Okay. This is where it really shows up with our strong guest nucleophiles. That's most of chapter 17. With the strong guest nucleophiles, they are so reactive, they need to react with the most positive thing humanly possible. Well, if we're going to look at our alpha beta unsaturated carbonyl structure, there are 2 electrophilic sites. Okay? Which of those would be the most positive? Well, the positive is due to a polarization. Polarization is due to the proximity near an electronegative element. Because oxygen is closer to our top one, that carbon becomes, quote unquote, more positive. So if we have a stupid strong or a strong guest nucleophile, it's going to lock in at the more positive position because it's trying to neutralize that negative charge of our nucleophile as quickly and efficiently as possible. If we just have a quote unquote strong nucleophile, and yes, we'll attempt to come up with some definitions for those, we'll end up seeing it attack the other position. Okay? And this one is a little bit less positive because it's further from that electronegative element. Okay? So why would a less strong nucleophile target the less positive? Well, something about attacking there is going to produce a more stable product. So really what we're evaluating is everybody's favorite conversation, kinetics and thermodynamics. So we really have to be thinking about how these 2 reactive sites differ as far as speed and as far as stability. Okay? This shows up in chapter 17 because of the Gilman reagent. Okay? The Gilman reagent is a negative carbon, but it is stabilized significantly to the point that it doesn't attack the more substituted, it attacks the less substituted. When we move into chapter 18, we really just see a lot of discussion of just the 1,2, and we don't really look at the conjugate additions anymore, but those nucleophiles are now all significantly weaker, and they would favor a 1,4 addition if we were presented in that situation. We just aren't in chapter 18. So this content straddles a little bit of a weird section because, well, it's blending both chapter 17 and 18, but it's only explicitly talked about in our chapter 17. Okay, so with that, we'll go ahead and continue on. What we're addressing is this idea of kinetics versus thermodynamics. So the first thing that we need to understand is which one is kinetic and which one is thermodynamic. Okay, so to do that, we have to do some kind of fancy math isn't quite right, but a little bit of careful footwork in analyzing our system. If we go through and look at this, the reactant's the same either pathway we take. Okay, be it a stupid strong nucleophile or a just strong nucleophile. Okay, so if we take a look at our kind of color coding within this, what I'm suggesting is that that red path is the 1,2 direct addition. Note where the nucleophile is attacking, directly into the carbonyl. Okay, the blue path is our 1,4 addition. So it's attacking at the indirect spot. Okay? It does still affect the carbonyl as seen by the resonance that comes out later on, and that's why they're tied. Okay? So how are we going to evaluate? So we look at our reactants, there's our difference. If we're going to try and decide now our intermediates and our products and how this balances out, that's kind of our next stage. So let's go through and kind of propagate this. Let's look at our intermediates. Okay, so this would really be our case of our intermediates. Is sitting in these. Okay. And why is that going to become important? Well, we're trying to look at those to decide how they would get placed as far as our reactions go. So we could call the blue one, God, it would have been nice if I'd done that. Intermediate conjugate, intermediate direct. Okay, so hopefully that makes a little bit of sense. If we were to look at our intermediates in that first kind of section, just here, we could go through and say, well, we have a negative oxygen versus a negative carbon. The negative oxygen is clearly more stable than the negative carbon, and that would be because the oxygen is more electronegative, right? But before we start getting into placement, we do have to acknowledge that our conjugate addition has a resonance option. And when I look at that resonance, I note that the negative charge sits on the oxygen. Okay? So if I'm now going to make a fair comparison between these, I need to be comparing these two structures to predict stability. Okay? And we now go through and do that. Well, they both have a negative charge on the oxygen, so it doesn't allow me to differentiate. So how would I decide which one was more stable? Okay, ID or ID or IC, okay, red or blue. Well, to figure that out, we would have to move to the next thing on the list. The next thing on the list would be looking at the most reactive thing in each of those structures. Okay, so let's simplify and get rid of that from our picture. Okay, well, what's the next most reactive thing in both of those structures? Hopefully you can acknowledge that it's the pi bond. Okay, that pi bond is higher in energy because it's p orbitals. Is there a difference in energy between those two pi bonds? Well, yeah, the bottom one is more substituted. The top one is less substituted. Because it is more substituted, from what we remember of first semester, that makes that intermediate more stable. Which means when we go down to our admittedly horrible labels of intermediate 1 and intermediate 2, we're going to expect that our 1,4, our intermediate conjugate, is going to be lower in energy than our intermediate direct. Okay? And that's really what we end up seeing. Depending on how you want to evaluate where you're falling on this, you could look at it with these, or you could look at it in a protonated state. It's not really going to make a difference, because when we continue to move through, when we protonate, our product is going to come out in that same color matching, because now really the only difference between those is the pi bonds. Okay, so if we look at that, that would really kind of suggest that we should only see the conjugate addition. Why would we ever see the direct addition? Okay, well, what we've shown here is the conjugate addition all the way down is the thermodynamic product. Dynamic, which means it's the lowest energy. The other one must therefore be the kinetic. Well, how do we differentiate kinetic versus thermodynamic? We have to look at activation barriers for the reactions. And this is what we talked about with the 1,2. That activation barrier is going from the reactant to our product. And what we're saying is that if we're seeing a differential here, it is because the activation barrier for the conjugate addition is greater than it is for the direct addition. Okay? And the reason being has to do with that polarization that we talked about. In the direct addition, that carbonyl carbon is more positive and therefore is more likely to react. It's a stronger interaction between that carbonyl carbon and our nucleophile than there is between the 4 position or our conjugate position with the nucleophile. Okay? So if we're thinking about speed, the direct addition makes the most sense. We're going to get the strongest interaction between those largest charges. So why would I differentiate between each of these pathways? So if we continue on, whoops, that's the wrong color for that one. If we continue on, we're not going to see a crossover. The crossover that we're talking about is right here, and that's the critical point on differentiating between these. So how does this now decide or help us decide which product to get? Well, it's all going to come down to the thermodynamic difference here, okay? That delta G. If that delta G is large, what happens to the reversibility of the kinetic reaction? So a large delta G would mean a delta G that's more like this. Well, the reversibility becomes very, very, very challenging, which means the only thing I get is the kinetic product. What about if that delta G is very, very, very small? Well, now that kinetic product can revert. Once it reverts, a small percentage goes through to form the thermodynamic and does the 1,4, but that thermodynamic reversibility is significantly less than the kinetic, which means I'm stuck in the thermodynamic path and I only get thermodynamic product. So the differentiation between these two pathways is really going to come down to, is the reaction reversible? And the more reversible it is, the more thermodynamic product I get. The less reversible that initial addition is, the more likely I see the kinetic. Okay? Why does this come back to our nucleophile? Okay, well, let's clean up a lot of that drawing. And what it's really going to come back to, and it's going to be most relevant to compare these here, is we said that our difference came in when we were looking at the strength of the nucleophile. And we said stupid strong nucleophiles did a 1,2. Well, a stupid strong nucleophile would be like a really big negative. So we're talking about H and most carbons. Okay? Well, that stupid strong nucleophile is going to follow that kinetic route. How do I decide if that reaction is reversible? To decide that reaction is reversible, I have to look at the stability of my most reactive species. So the intermediate is a negative oxygen compared to my nucleophile, a negative hydrogen. Which one is better at holding that charge? Well, the oxygen, right? Which means this reaction drives towards the oxygen and I don't see a reversibility, right? In the 1,2 addition, this reaction is irreversible. If I move to a weaker nucleophile, let's say O minus, well, now what happens? I'm going to compare that negative oxygen to a negative oxygen. Well, they have roughly the same stability. If they have the same stability, that reaction becomes reversible, okay? Which then means the 1,2 addition is reversible, and I can now form the thermodynamic. Because the thermodynamic is a lower energy intermediate or product, it doesn't reverse, and I get only that as the potential product. So all of this is really hinging on our ability to predict reversibility of an individual reaction. Okay? That reversibility can become a challenging thing for students to process, but that is something you've already done. Okay? You did that when you looked at 152. If we look at this reaction, how do we decide which side of the equation is favored? Okay? And not the bottom one, the top one. Okay? We're looking at a standard acid-base reaction. Okay? This species acted as the acid, and I know that because when I look at its conjugate on the other side, the thing most like it, it lost a hydrogen. So that becomes the conjugate base. This is my base. This becomes the conjugate acid. Well, how do I predict which way that equilibrium should favor if I look in here? Okay? Which way should it go? Well, how do I know that? What should I be evaluating? Well, in theory, what you remember from 152 is that we could predict that using pKa's. So we could compare the pKa of our acid on each side of the equation. The acid over here is a 4.2. The acid over here is a negative 1.3. The smaller the pKa, the more acidic. Reactions favor weaker substances. We favor neutrality, which means this equilibrium favored reactants. Okay, so we could use pKa's in 152 to go through and predict these things. This is why I tell you that pKa's can be useful to memorize, because it can help you predict this. But I also said that you don't need to have the pKa's memorized, because the other thing that you could use to evaluate this process is looking at organic chemistry, which is ultimately the electrons. The electrons tend to be easiest to discover in the bases. And when we go through and compare these bases, we're looking at the oxygen's lone pair electrons on water versus the oxygen lone pair electrons on the acetate, which is formally negative. Which of those two is more stable? Okay? That stability question is a challenging one, and students tend to kind of forget that we use this. Okay? This is why there's that video called Reactivity of Things. This is why you're told to memorize Cario, which I don't like personally, but what we're talking about is how do we evaluate a stability? And it turns out that organic chemists looked at these pKa's and said, well, we could look at it in a different point of view. We could look at it as from the point of view of the electrons, and we don't have to quantify it because we know that charge very often is exceptionally reactive. So I'll look for charge first. After charge, I'll look at the atom size that's holding charge. After the atom size, I'll look to atom electronegativity. Then I'll look at resonance. Then I'll look at induction. Okay? And then if I have to, I'll dig down into all sorts of things. Hybridization. Okay, substitution patterns, like how many things are on it. We saw that when we're looking at our double bonds. So those are all qualitative comparisons that an organic chemist uses to predict which way a reaction is going to run, okay, without having to quantify it using the pKa's. Okay? There are some cases where the qualitative observations don't work. Okay? For instance, you could go into the store and buy an apple and be like, well, dang, that red apple looks really tasty because look at how bright and red it is. That must be awesome, awesomely flavorful. Okay? But somebody went through and literally designed that apple to look beautiful so that you bought it, but it tastes like crap. That's the origin of the red delicious apple. Feel free to look it up. It's actually true. Right? So there are exceptions. And it's not a malicious exception, but there are exceptions to using those qualitative rules. When you hit those exceptions, those would be things you should memorize instead of memorizing everything. Okay? So if we go back to our reaction that we're running, we can run that same kind of argument. Let's pick some nucleophiles. Let's pick H-. If I run H- through this reaction, what would I expect to happen with this equilibrium? Right, well, I would look at my product. I'm looking at O- versus H-. Well, which one's more stable? Okay, they're both charged, so that doesn't help. I could move to size. In this case, we do see a difference in size because hydrogen and oxygen are in different rows. Hydrogen is really, really, really small, which means it can't stabilize that charge very well, which means the oxygen is more stable. This reaction drives heavily towards the reactants. That's not reactants, that's products. Drives heavily towards the right, okay, for our products. And we can do that based off of those charges. Are there other ways that we could evaluate it based off of pKa's? Yes, but it becomes really challenging in this case because we aren't running an acid-base reaction. Okay, so we'd really have to be using pKb's, and I don't know how much you remember from 152, but for sure the conversion back and forth between A's and B's was just a nightmare for me personally, and I prefer to not have to think about it in that process. Okay, So that's just kind of my 2 cents. But that's really what we're evaluating here. We can dig in and look at those pKa's and try and evaluate them, but it really isn't critical in this case, right? And because it's not an acid-base reaction, using pKa's is not really helpful, okay? So we've got our reaction set up. Note our pretty diagram. See the kind of shifts in those energy diagrams. If we looked at hydrogen as a nucleophile, its pKa would be really, really, really big, which means its pKb is really, 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 really small. So if we're looking at that kind of difference, we're seeing a drastic difference in those pKa's and not in a way that favors the reaction. And so we see a pretty close equilibrium between these. And this reaction here, the kinetic product becomes, whoops, we see a large difference in this. And so this reaction for our kinetic becomes irreversible. So we would refer to H- as a nucleophile as an irreversible nucleophile that leads to a kinetic product. Okay, what was our kinetic product? The kinetic product was the direct addition, so that would be a 1,2 direct addition. Okay, so all of those pieces associate through this. Okay, what can become confusing is where you're placing that irreversible. That irreversible is tied to the nucleophile or base. It is not tied to kinetic or 1,2 direct addition, as we'll see here in just a second. Let's switch it up to a different nucleophile. Let's go with, let's just say H2O, pKa about 16. Okay, it's 15.7, but it's about 16. If we look at that, how does that end up changing that reaction? Well, with that nucleophile, the delta G between our reactants and our intermediate is now very, very small. So that kinetic product is still going to form first, but it is now reversible. Okay? Reversible with our H2O, okay? Or even our OH minus for that matter. Okay, why does that become problematic? Well, if it's reversible, the kinetic product reverts back to the reactants. A small amount makes it to the thermodynamic, but now the thermodynamic is not reversible, and I get the thermodynamic product, which would be the 1,4 conjugate addition. If we tie reversible to thermodynamic, we immediately run into an issue because we're looking at different aspects, okay? Reversible isn't thermodynamic because the thermodynamic was irreversible, okay? The term reversible and irreversible is more specific to the nucleophile or base that's running in our reaction. The thermodynamic or kinetic is a conclusion of that statement, okay, or of that analysis, okay? If we were to go through and kind of propagate this out, we could look at a bunch of different pKa's and see these relationships. Note there's some exceptions. So when we move down, we have a carbon nucleophile that follows under the same kind of pattern as our hydrogen, okay, being significantly larger than our OH, okay, because that was our intermediate. But if we go down to the cyanide, whoops, that's me scribbling it out. That nucleophile, the pKa significantly changes. That significant change in the pKa means that this one becomes reversible, and we would see conjugate addition, not direct addition. So typically, carbon's going to be a direct addition because it is stupidly strong. It can't stabilize that negative charge well. There are some carbon structures that can stabilize that charge. Those, I would argue, are exceptions to the rule and therefore should be memorized. Cyanide should do a 1,4 addition because it is stabilized. Why is the cyanide stabilized? Okay, well, the cyanide is stabilized because what's it connected to? That negative carbon is stabilized because it is next to an exceptionally electronegative nitrogen, right? And that's what's causing that drastic kind of change in the pKa value or the reversibility, irreversibility of our individual species, okay? Your textbook has this kind of nice table that sorts out a lot of, but not all of, our reversible versus irreversible. Notice again, what they're referencing is not kinetic or thermodynamic, they're referencing the nucleophile. So if we look at nucleophiles that add irreversibly, we've got the Grignard, which is a carbon. We've got the alkyl lithium, which is a carbon. We've got the Wittig, which is a carbon. We've got lithium aluminum hydride, which is a hydrogen. We've got sodium borohydride, which is a hydrogen. Note, in all those cases, those are species that don't typically hold negative charges because they can't stabilize them well. If we look at the ones that added reversibly, okay, what's different about those? Well, we've got oxygen, we've got nitrogen, we've got our halogens, okay, we've got oxygen, we've got carbon, and we've got carbon. So let's leave those two off for the moment. And if we look at the general trend for these, is that those are all species that can hold a negative charge because they're electronegative enough to hold them, right? And that's what's allowing it to add reversibly. If we look at the bottom cases, those ones I would argue should be falling in that kind of exception category, okay? Because you're looking at carbon. Why are those carbons reversible? They're reversible because we have some secondary effect that's kind of distanced from the carbon, but is significant enough to change the carbon's reactivity. Okay? So those should get memorized as reversible because they're exceptions to the pattern that we're seeing. The rest, you shouldn't have to memorize because you can apply the logic behind it. Right? Those nucleophiles will add reversibly because they are roughly the same stability as the intermediate. That means that delta G shrinks. Okay. This is an incomplete list, and I think we'll actually see that pop up on our very next slide. And now my device isn't connecting nicely, which is going to make a big mess for me, but we'll try and do an escape there. And yes, I apologize for some weirdness here. And I'm just going to hope my device connects up. So if we go through and look at some potential example questions as a delay tactic, we want to decide which product should I get. So if you were to see this as a multiple choice, we could ask the question, what's the product? A, B. Okay, we'd probably also throw in a C and a D of, I don't know off the top of my head, but we'd get something else in there. Okay. So you would be responsible for trying to differentiate which product you get. And conveniently enough, we missed some hidden information. So how would we decide which one it was? So first and foremost, you should acknowledge that we have this conjugated pi system. Okay? How we know it's conjugated because there is a single sigma bond between those two pi bonds. Okay? And it's not just double bonds. This would not apply for the conjugate addition, okay? Because those two pi bonds are the same. We need a non-polar pi bond. So we'll typically see it with the carbonyl. That's why the alpha beta unsaturated ketone. But as long as you have a polar pi bond that is conjugated with another or with a non-polar pi bond, you now have this potential for conjugate additions. So if we're going to go through and try and predict how this is going to happen, you need to decide which one are you going to get. Are you going to get, and I just forgot something that we needed to address, which we'll look at here in a second. Okay, are we going to get the conjugate addition or direct addition? So the first thing we should do, here's our nucleophile. If we look for this first one, we did the conjugate addition. Okay, so this would be a conjugate addition. And the next one did the direct addition. Okay, so we've got that nailed down. Okay, so how should we decide which one we should get? Well, we have to remember that in our first step, either way we do this, we're going to get a negative charge on that oxygen. So what we need to consider is the stability difference between that oxygen and our nucleophilic negative carbon. Okay, well, which one's more stable? The oxygen. Since the oxygen is a product, this reaction would heavily drive towards our products. Okay? Since it's heavily driving towards our products, and I color-coded this backwards and it really irritates me, we would expect the kinetic product to form first, which is our direct addition, and that should be irreversible. Okay? So what we're doing is saying that our nucleophile is an irreversible, which means I only get the kinetic product. Okay? Because I've labeled these according to their additions, there's my product and I'm done. Okay? This would be the one in highest percentage. I think I wanted a different word, but I can't think of that word. Okay? If we look at our change, we have a 1-2 addition. So 1-2 direct addition. We'll look at the other one in a second. Okay, so now let's look at the one underneath. So we'll run the same color coding. Okay. Remember, in all of these cases here, these are all going to go to a negative oxygen intermediate. When we look at the reactant we're reacting this with, here's our nucleophile. Okay, we have a negative oxygen in comparison to negative oxygen. That is reversible. Okay. If it is reversible, I would expect the thermodynamic. Okay, because the kinetic will form first, but now it can revert. So if we go back and look at these, direct, because of where that nucleophile is connected. Our conjugate, this is a thermo, this is a kinetic. Because it is reversible, I would expect that kinetic to form first and then reverse, leading to me to only the thermodynamic. Okay? And so what I'm doing is trying to piece through each of them. Because we now have a new product to look at, remember we called the conjugate a 1,4. If we go through and look at the change from reactant to product, we put something for sure at that 1, but we also put something there. Why is this called a 1,4? The 1,4 comes from the fact that after we do that addition, definitely should have talked about this earlier. When we do our first addition, we have the negative, double bond, and then our nucleophile. With that negative, that's when we would put on our hydrogen. And if we compared 1, 2, 3, 4, okay, that would be the 1,4 addition. Okay, so one of the C answers could be that structure. Okay, you say, well, why would that answer be wrong and the blue circled one be right? Okay, the blue circled one is right because we have an alcohol next to an alkene, and we have an enol, and enols immediately tautomerize to the ketone or to the carbonyl structure. Okay, so yes, that's confusing, when you look at the placement of atoms, but you have to think back to how that reaction is running. Once you form the enol, you're pushing another reaction that hides that 1,4 label. Okay? The last one, I'll leave you to go through and decide and work through. And if you have questions about it, you can send me an email, post to Piazza and ask, say, hey, this is the one that I think it was. And we can discuss that as far as reasoning. Okay? With that, we're getting really, really long in the tooth as far as this video goes, but I do want to address Gilman reagents. If we looked at that last one, we might go through and evaluate that with that nucleophile, we have a stupidly strong negative because lithium is not good at stabilizing that, and that could favor a different product. But thanks to Mr. Gilman here, what he noted was that probably by accident, that when he took this butyl lithium or the lithium structure, and there was a little bit of copper present in his reaction, and in fact, I believe it's actually a copper iodide, he noted that what he got was the indirect, okay, the conjugate addition. Okay, so why? So if we look at the reagent, oops, because I need this button, and I'll fix that typo right now. So if we look at that, the copper structure can insert itself between the carbon and the lithium, similar to a Grignard reagent. Okay, so we still have an ionic bond here. So we might consider again that that carbon is now stupidly strong, and so should get me the direct addition. And instead, it gets me the conjugate addition, okay, or my indirect. And that is very puzzling. Okay, so why should that happen? Well, to really drill down into that, you would have to address what is the difference between the Grignard and the Gilman. The Grignard was a carbon next to a magnesium. The Gilman is a carbon next to a copper. Well, really that only difference is coming back to magnesium versus copper, and the difference in electronegativity between carbon and magnesium is significantly larger, so large in fact that that makes that carbon incredibly negative. In the Gilman reagent, because copper is closer to the carbon, the difference in electronegativity isn't so great, which means that carbon's negative isn't so large, which means it's not large enough to clear that threshold between our conjugate and direct, or it's enough to clear that threshold into now a slightly weaker negative, and we get the conjugate addition as opposed to the direct addition. That kind of sucks because you just have to memorize it. Yeah, anything on those thresholds between one product or another, whether defining that line or walking that line, yeah, those are going to be memorizations, unfortunately. And so with the Gilman reagent, you do need to memorize it. As far as how you can see it, you can see it as shown, okay, in this particular reaction, where we've got the carbon next to the copper and lithium. Note that you get two equivalents of the carbon. Or you could see it written out where you're taking your CH3, CH2 lithium, so your alkyl lithium structure, and then you react that with, I'm fairly certain it's copper iodide. Those two together make the Gilman. You can then react the Gilman with your alpha beta unsaturated carbonyl. Okay. One of the other things that makes the Gilman reagent interesting is it's not strong enough to attack a carbonyl on its own. The Gilman reagent will only attack the unsaturated position. Okay, the alpha beta ketone will only get that conjugate addition. It will never attack the carbonyl, which is kind of neat. Okay, and I believe technically with that, yeah, we're done. Okay, so I know that was a long one. I apologize. So I'm going to go ahead and stop that. If you've got questions, that is a very difficult lecture. Please start up some discussions in the discussion board, or send me emails, or talk to your classmates, because it is a rough one to differentiate those.